everyone. So in this tutorial or in this video, what I'm going to show you is how to do a uh, GROMACS simulation from start to end. So this is very simple example that I'm going to do here. So it's just going to be lysozyme in water. So what will happen to lysozyme when you put that protein in water? So this is like a classical like example that you can do on GROMACS, and in this video I'm going to show you how to do this from the start. So you do not need to know anything prior rather than having GROMACS on your computer. So if you don't have GROMACS on your computer, so please look at my other video, like the previous video that I show you how to install GROMACS using Homebrew to your MacBook. Yeah. So the first thing, so this tutorial is um, I use this tutorial from this Benvenlab group. So I show you this Benvenlab. So Benvenlab GROMACS tutorials. So I'm going to do this first tutorial for you. I'm going to show you how to do it. Okay. All right. Let's get to it. So the first thing that we have to do is we have to download the protein. So in this tutorial, the protein that we are using is lysozyme. So to download the protein, we need a .pdb file. So to get that file, we need to go to the PDB data bank, or the protein data bank. So we can type here protein data bank, and then we go to this data bank, and then we need to find lysozyme, or here they call it 1-AKI right here. So I will simply search here 1-AKI. Okay, so it's a lysozyme, right? So I download files and go to the PDB format, and then it downloaded a PDB file and paste it in my desktop. Okay, so to make everything clear, so I'm just gonna make like a new folder called lysozyme in water, right? So I'm just gonna put this file in this folder. Okay, so that's the folder that we have, the PDB file, right? So this is, you can open this as a text file. So it has a bunch of data on it. So you can, they basically describe the protein for you in numerically. So you can open up the file and look at it, and you can go to the GROMACS manual to see or PDB manual to see what each line of that file represents. And then the next step is we have to go to the terminal. So I can get the terminal from here, and then I have to go to this folder, so lysozyme in water folder. So in Mac I put ls, so then I go to the CD desktop, right, list again, and then I have to go to the lysozyme in water folder. So just copy paste the name. So now we have that file, so 1-AKI.pdb. Okay, so the first thing is we have to set up the PDB file, right? So we have to convert that PDB file to a GRO file. So what we do is we do GMX PDB to GMX, and then dash F. F means the file that we are looking at is 1aki.pdb. You have to type these letters. It's case sensitive, so you have to type it as it is, and then dash O. So output, we need 1aki processed dot gro. So we are giving a gro file, and then so this is the water that we are going to use, SPCE water, and then we hit enter. So then now it asks from us what force field that we need to use. So this is a very important question. So the force field is a backbone of your simulation, so a backbone of your molecular dynamic simulation basically. So you need to have a good understanding of these force fields. So in this tutorial, as this is a simple tutorial, so we are going to use OPLS, all atom force field, which is 15, but there are different other force fields available for you. There are Martinov force fields, those are coarse grain force field, the Amber force field, Charm force fields, GROMOS, the GROMACS, their own force field. So if you go to the GROMACS manual, and then it will show you what are the force fields available in GROMACS and how you can incorporate other force fields into GROMACS, and how to use it. Okay, so in this tutorial we are just going to use number 15. So we have to type number 15 and hit enter. Okay, now what happened is, now we have in chain 1 we have 1960 atoms and 129 residues, and in chain 2 we have 234 atoms and 78 residues. Okay, now total mass in the system is 15,718.394 atomic mass units, right? So we have a total charge in the system is 8. Okay, we have a charge in the system. So now we have a GRO file, right? So in this step, if you go to your folder, you should be able to see other two folders, other two files created. So it's .itp file and a .top file. So it's a topology file, and then we have the position restriction file. So so I'm not going to give brief descriptions on these things. If you go to the GROMACS manual, you can basically read it through, and yeah. So let me know if you have any questions in comments. So you can always open these files as text files and see what's inside what is inside these files. So topology file is basically, that's the initial topology of the protein. So the coordinates of the protein that we are going to use. So starting coordinates of the protein. Okay. So if you open up the topology file, you can see the x, y, and z coordinates of the initial coordinates of this protein. In this case, is lysozyme. So next one, we have to set up a box for our simulation, because we can't run infinite simulation. So we have to create a box to run our simulation. So how do we do that? Is we run this command, so gmx, and then we use edit conf, and then -f, and then now we are looking at our GRO file, so processed.gro, 1aki processed.gro, and then we are outputting 1aki new box. That's to say that we created a box, so another GRO file with the box, and then -c means put it in the center. We have to put the protein in the center with the distance dash d from 1.011 nanometer from either side, and the box type is dash BD means a box type. I need a cubic box. You can either go for a different type of box shape. So here, because we are doing a simple simulation, so we're just going to use a cubic box shape. Hit enter. So now it created a box, right? So you can see the dimensions of your box. So you can see that so you see the box vectors and box angles, box volume, and the center of the box and all of these things. So I would highly suggest, if you're doing GROMACS for the first time, please go through all of these details that they're going to show up in your terminal. And these are the very valuable information they're going to tell you. Okay, so the box now that we created has a cubic nanometers of 395.33 cubic nanometers. Okay, and yeah, so the GROMACS also gives you some jokes. So yeah, and then so the next step is to we have to solvate the atoms, right? So we have to put like like we have to put a water, or we have to solvate the atoms. So how do we do it is we use GMX solvate C-CP. So it's looking at the protein file now, and then yeah, 1AKI new box dot gro and dash cs. Use SPC216. That's the water GRO file that we're going to use, and then we had output 1AKI solve.gro, and then we have to update the topology, the initial topology after we putting the water molecules in there. So that's the dash p, and then we go top pol dot top. Okay. Yeah. So now we added water molecules into our box. Okay, so if you're confused with what is this dash CP and dash CS, so the best way to learn these things is go to the GROMACS manual, and it will literally show you what are these commands means. Okay, so it's best to go to the manual and find it out. So now we put new solvent configuration of 4 by 4 by 4 boxes. So box contains 45,472 atoms in 13,824 residues. So, and then you can see that we have lots of atoms in here, right? So that's why GROMACS takes so much computational power to do all the calculation, because there are so many atoms that you have to do calculations, right? So the next step now, we need to put ions into our system, right? So to put the ions, why we are putting ions? So we are putting ions in order to neutralize the system, because we can't have charges in our body. There it's neutral, right? So we have to put, so in here I think I showed you like the first time when we created the GRO file, there it gives us a charge as 8. Now we have to neutralize it. Okay, so how do we do it is we have to put ions into it in order to neutralize. Okay, so to do this we need a .mdp file. Okay, so how do we get this thing? Okay, so let's go to the tutorial. .mdb file. So Okay, so here, so we have to create a .mdb file, and they given us an example of a .mdb file. Let me open it as a separate window. So here, what they basically have is all the necessary commands to run the simulation. So that's why we have an MDB file. Okay, so what I would basically do is you can save this information as an MDP file, or you can basically copy this, and you go to your terminal. You can type nano. Now we have to create a folder, so we got folder name is ions.mdp, and it gives you this screen. So you paste it and you put Control X and then Y and then enter. So now if you list it again, now you have ions MDP file now in your folder. Now you created this folder. Now you have to give this command GMX gromp, looking at -f ions dot mdp -c 1 AKI solve dot gro and -p, and update the topology file, and then I need the output of ions.tpr. Okay, I do that, and then now I created a TPR file. Now I need to put ions into my box. So GMX, so gen ion is the command that we're going to use. So -s ions.tpr output 1 AKI dot solve dash ions dot gro. So it's a new gro file. I have to update my topology, so topo.top, and then positive ions name is Na, and then negative ion name is Cl, and then number of ions is 8 because we had a charge of 8. And then it asking what group I need, the solution group. So I need like the group 13. I need SOL. Okay, now we have 8. So 8 solid molecules in topology file was replaced by 8 Cl ions. Okay, so now our system is neutralized. Now we have to relax the file because now we added ions, we added water, so now we have to relax it, right? So we have to energy minimize. So now this is the energy minimization step. In this step also we need a MDP file. Okay, so what we're going to do is again going to go to the tutorial. Now it is the energy minimization step. Okay, now we can, so this is for the to create another TPR file for the energy minimization. Okay, so copy that. Now you can go to nano em.mdp, copy paste, Control X, Y, and enter. If you list it, you have a em.mdp file. Now run the GMX gromp command, and then I'm looking at the em.mdp, and then enter 1aki solve ions.gro. Okay, that's this, and then I can go to the update my topology file. So every time you do something, you have to update your topology, right? To update your coordinates. So output em.tpr, right? So you do that. Okay, now we created a TPR. Now we are running a simulation. So now we are going to run like a simulation. So GMX md run minus v, so we can see the steps, and def em. It will run a energy minimization simulation. It's basically doing the energy minimization for you. Okay, and the next steps, we have to equilibrate the system. So it's NVT and NPT, and then after that we can do the final MD run, the production run. Okay, so this might take a couple of minutes depending on your computer power. So I have old computer, so this might take a couple of minutes. Okay. Alright guys, so it is done. So now we have to do NVT. Okay, so now for this also we need an MDP file. So we are going to we have to get another nvt.mdp file, right? So how do we do that? So let's go to the tutorial and see. Okay, you can, if you want, you can see the energy minimization chart. You just copy that, and then you just copy paste here. Right, now we need so to get the MDB file, we can copy paste this, and copy, and then you go to your nano nvt.mdp, copy paste, Control X, Y, list it. Now we have, where is our MDP file? We should have nvt.mdp, yeah, right here. So now we have MDP file. Now we can do GMX gromp. So I'm not just gonna copy paste this, so I just type it from the script. So GMX gromp minus f, like dash f, nvt.mdp dash c em.gro, and then we do dash r em.gro dash p update the topology file, and then output nvt.tpr. Now we run another small simulation for the equilibration, so md run. Okay, yeah, so this might take a couple of minutes, and then next step is to do mpt. Okay, let me look at the mpt. So we need a mdp file for that too. Okay, so that's mdp is here. So these are all the commands that you need to run your md1. So you can see the title, OPLS, Lysozyme MPT Equilibration, and then you can integrator, MD, and a certain number of steps, 50,000, and then you can see all of the different variables that you can give it to your simulation. I'm into your MD1. And then, so this is gonna take a couple of minutes. Let's wait. Alright guys, that NVT simulation is already done. Now we have to do NPT simulation. So for this also we need a MDP file, right? So how do we get that MDP file? So I go to the tutorial, and here they give us like an example of the MDP file that we can download for our MPT equilibrations. Okay, here it is. So I copy, and then I go here, say nano mpt.mdp. That's the file we need. Let me make it bigger, and then I copy paste, Control X, Y, and enter. Okay, now if you list the files, you can see that we have npt.mdp. Okay, so where is it? mpt.mdp. Okay, now I have to give the gromp command, so which is gmx gromp looking at in there. So yeah, so now it's done. So we created a tpr file. So, and then we run the equilibration phase 2 for the MPT. So we do this. Okay, this is gonna take a similar amount of time that we took for the last one. Okay, so I will see you guys in a few minutes. So the MPT is done now. Now you can see how much time it took and the performance and all that. So now we are ready to do our production run. Okay, so to do the production run, what we have to do, we have to have another MDP file, right? So how do we get that MDP file? We go to the tutorial, and then we go to the production run, and then we need another MDP file. So copy, and then now I'm gonna say nano md.mdp, paste, Control Z, Y, and enter. If you list, you have md.mdp right here. Okay, now we have to make a tpr file, right? Like the same thing that we did before. So gmx and grompp gromp, and we go -f md.mdp -c npt.gro, and then t-t npt.cpt, and then update the topology -p top4.top output md 01.tpr. Okay, and now this can generate the TPR file. So the TPR file is generated. Now we are finally going to do the production run. Okay, GMX MD1, the production run, we can't see the steps. MD 0. Yeah. Now this this might take a lot of time. So I will see you guys soon. So the final production run is completed. Now after that production run, we get so many files loaded into our folder. So I will make a different YouTube video to show you how to install VMD and how to use VMD in order to visualize the results. So here I already made like a small animation that came out of from VMD just to show you how the protein looks like after our simulation. And also I just show you like a screenshot of shot I got from the VMD uh, simulation. So these are the water molecules, and the blue one is the protein that we put it in the center. And let me show you how just the protein animation of the protein reacts with water. So it just vibrates, right? So when it reacts with water, so in the VMD you can change its cartoon into the licorice forms or bond form. That's a separate video to discuss. This video is already too long. So I hope you guys enjoy the video. Please subscribe to my channel, and I'm hoping to put more tutorial videos on GROMACS to this YouTube channel. Thank you.